All right, crew. So today or tonight, I'm going to be talking to you about the dihybrid cross. And what's important here is to distinguish this from today's monohybrid cross. And if you look at your notes from today, you'll see that the monohybrid cross is named because you're looking at one trait, which is the mono piece, which really simplifies things greatly. And then you're looking at the situation where the two alleles are different, where it's heterozygous for that particular trait. Okay, so heterozygous. Good, Abigail. Okay, so now what we're going to do, okay, Lumpy, I'll be there in 10 seconds,
Okay.
is we're going to look at the dihybrid cross. And of course, Abigail, what does the prefix of di mean? It means two. So we're looking at two traits in their hybrid form. That is two. Bi and di are the same prefix meaning. So when you're looking at two traits, it becomes suddenly much more complex, particularly as we start to focus in on making the gametes. So imagine here we're talking about this is a germ cell. It can be in a male or a female. It really makes no difference. And you have here actually, I should make this a little bit bigger there. You have a chromosome from dad, a chromosome from mom. And since we're dealing with two traits, let's assume for a moment that these traits are actually on different chromosomes. So I have another chromosome from mom. It's a little bit smaller there, so it's a higher number. And then the matching chromosome from dad. And I'm going to go ahead and use a green dot to indicate the one trait, and I'm going to do a yellow dot on mom's. Okay. Oh, that's not yellow. There we go. Yellow for mom right there. Notice it's in the same gene location, so that means we're talking about the same gene locus, but a different allele. And then on the dads, I'm going to go, let's say, I'll do red over here. And on the mom, I'll make it, why not make it a little purple action going on right here. Same again, gene locus, but different allele. Now, it's very important to understand that each of these things would undergo duplication, right? And as a result of undergoing duplication, they'd be connected to each other. I'm not quite sure if I can make this happen. Yeah, well, sort of like, oh, that's crappy. Just make it like that. There we go. They connect to each other. And the reason that's important is that we're going to now have each of these things duplicated. I'm just going to pause and duplicate these all right now. All right, now to simplify this, we can all see that we've got a whole bunch of things going on here. But let's simplify this a little bit. I'm going to assign for this green guys over here, I'm going to say that this is a big R. Oh, that's too fat. Hold on, let me undo that. Let's see if I can get a skinnier thickness. Okay, I'm going to do this as two big R's, and then the mom is lowercase r, lowercase r. Oh, cool, lumps. And then on the other trait that we're looking at, I'm going to do D, and I'll make this two capital D's, and this two lowercase d's. All right, so this is happening inside the germ cell of either a male or a female. Now, don't forget that when we're all said and done, we are going to be able to produce 4 different cells, 4 gametes for each one of these. Of course, some of them could be a polar body rather than being a viable cell. But let's just for a moment say that they're all going to be potentially viable. Now, you know that you need to have one of these chromosomes in each one of these things. I'm sorry, 2 of them. So it's going to be one long one and one short one in each of these chromosomes. So if I just go with the letters rather than drawing the squiggles, I could have one combination where I take dad's long blue, which would be the capital R, okay, and I combine that with, let's go with, when I say dad's, I mean the one that was contributed by the father of this person. And then I'm going to go with the dad's lowercase d, right there. And then I'm going to choose on my next one, I'm going to go back with the capital R, but this time I'm going to go with a capital D. This would be for if I were to select one of these into my final gamete. And then for the other one, I'm going to go now to a lowercase r, and I'm going to combine that with a lowercase d. Again, that would be taking from this little guy right there. And I'm going to go again with lowercase r, but this time I'm going with the uppercase D chromosome that would come into that particular gamete. So we can see here as a result of this, and I'm just going to make these sperm to make it a little bit easier. Out of this germ cell, there are 4 different types of gametes that can be produced. Right? That's the only 4, because you can't have 2 capital R's. If you have 2 capital R's, then you're not going to have, that means you're only taking from this chromosome, whoops, didn't mean that, this chromosome right here and this chromosome. You have to take one of these and, either this one or this one, and then you have to take one of these, either this one or this one. Because in your final gamete, you have to have one of these long guys and one of these short guy chromosomes. Do you understand that? You could never have a capital R with a lowercase r or a capital D with a lowercase d in this particular situation that we're setting up. It may take you a little bit of time to fathom what's going on there, but that's a very important thing to understand what's going on here. All right, so anyway, because of random chromosomal shuffling, these are the different combinations that you get. You have a 25% chance of getting any one of these combinations in your sperm, or eggs as the case may be. Now that's going to be vital, because now we're going to imagine that I take an individual, and let's change the letters here. I'm going to go, let's decide, you know what, actually I have to go carve pumpkins. I'm just going to write a note here that says start the cross with the parentals. Okay, and you'll understand what that, I'll get to that in a moment. This is just my notes to self. Okay, I'll be back in a little bit. Okay, so the parental cross here, I want to start off with the purebred situation. So let's go with, I'm going to do, let's imagine there's a trait for dumb and another trait for ugliness. Okay, so we're going to say that being dumb is dominant to being smart. Okay, actually let me erase that for a moment. So this equals being dumb, lowercase d, smart. Okay, and then we're going to do capital B for beautiful, and lowercase b for ugly. Now obviously there are not genes for dumbness and beauty, so just keep that in your brain, that there's no way that that could possibly be the case, but I'm doing it just for absolute hilarity and comic relief here. So let's say we have a man who is purebred for dumbness and also purebred for being beautiful. And we cross that man with a female who's purebred for being smart, and she's also purebred for being hideously ugly. Comes from a long line of ugly people. So if this is the case, I think this is a much easier solution in terms of what's in the sperm, because the sperm's going to have, you have to have a gene for your brains and a gene for how you look. And in this case, if you're the guy, all you can do is provide a capital D and also a capital B in your sperm. And then the egg, all you can provide here is the lowercase d and the lowercase b. So that means when you do this cross, And I could do this in a Punnett square, but I think you probably, I can probably afford to skip this with you guys doing the Punnett square here, because you would know that if you combined this sperm with this egg, you would end up with a capital D and a lowercase d, and a capital B and a lowercase b. And this would be the first cell for the child that came about through the conception of this dumb, beautiful guy crossed with this smart, ugly woman. Okay, so there you go. And of course, every time they were to have children, they'd have dumb, beautiful children. Every single one of them, no matter what. Because dumbness is dominant over smartness, and beautiful is dominant over ugly. So 100% of their kids. Now let's imagine we do what we did today in class, and we cross two hybrids with one another. So we take this combination and cross it with that. So we have the male over here, let's say the female over here. Now don't forget that we have a scenario that looks a lot like what we had, where is it? Where did I put these things? Right here, okay? Where now with the hybrids, we have 4 different types of sperm that can be produced. Whereas, don't forget, over here, whoops, where's my undo? Over here, we only had, with the purebred cross, 1 type of sperm that could be produced and 1 type of egg that could be produced. Now we have 4. And that makes things a great deal more complex. So let's take this right here, this piece right here. Let's go to another page and start fresh. So, again we have, oh, actually I don't want to do that. We have a dumb, beautiful, crossed with another dumb, beautiful, and they're both hybrids. And since we're dealing with 2 traits, this is going to be a dihybrid, just like I mentioned over here, the concept of the dihybrid cross. All right? So we have this dihybrid cross that we're going to do here. And let's take a look at the different sperm and the different eggs. So if this is the male and the female, I want you to take a moment and pause this, and I want you to think about what the different gametes could be when you have this combination, when you have this paired genotype here. All right, so take a moment and then pause it, and then come back and see what I have and see if you were right. All right, that's what I hope you got. There are the 4 different type of gametes from the dad, so the 4 different sperm you could have. Like, yeah, oops, I got it here. This dude, and this dude. Those are 4 different ones. One, always representing a brain gene and a looks gene. And then you could imagine we have the exact same thing going on over here with the female. Right? It's going to be the same combination, no surprise there. And of course, since it's an egg, one of these is going to be selected 25% of the time. So let's see how this works out when we do the actual table. Let me set up the table first, and then I'll come back on. Let's see, I think I'm going to go to a new page. Okay, so this is a great deal more complex than we saw with the monohybrid cross. We have a 5x5 grid, and just like we saw though with the monohybrid cross, we're still going to have this area right here. This is the gamete boxes, and then this is the set of gamete boxes too. So let me just, I'm going to put the male gametes up here, and I'm going to put the female gametes down here.
Sorry, home slice. Can you try that again in fewer words?
Wow, I didn't say anything to you, Siri. Why are you responding to me? That's strange. Siri's talking to me for no reason. And then I'm going to go ahead and I'm going to put in the gametes into each of these situations. And we have big D and big B. And then we have big D, little b. little d, big, and then both recessives coming in there. And I'm going to do the exact same thing for the female. I'm going to pause it so I save some time here. Okay, this is what you should have. And now I want you to take a moment to fill in all the different combinations that could potentially occur through fertilization. I'm going to do one of these just so you know how to do this and keep it all straight, because it makes it a lot easier if you can sort of logistically put this together. You always want to put the same letters together and pair them up. So for example, let's say I'm looking at this region right here. I want to do the two D's together like that, and then the two B's together like so. So that box is going to be, that would be, if that combination of the sperm here, oh, I didn't mean that, this sperm right here with this egg right here would produce this zygote right there. So this child would be dumb and ugly. Great combination, right? Now I want you to hit the pause button. I want you to fill this all out yourself and see when you come back if this is what you have. Okay? So this is what I came up with. I want you to notice that, don't forget, the parents were, they originally started off looking like this right here. Big D, big B, little b. And you can see here that we have some children that also follow that, like right here. Big D, big B, little b. And here's another one over here, right? Here's another one right here. Here's another one right there, right? So there are some who actually share the exact same genotype as their parents. But what's important now is to go through and figure out what the phenotype is for each of these things. No. They are the same genotype. Did I say that wrong? Oh, well, they actually are the same phenotype as their parents as well. Yeah. Okay, so I want to scooch over here because I want you to notice that I'm going to color this square in with a black little triangle here. And the little black triangle will represent all those that are dumb and ugly in terms of their phenotype. So we have dumb and ugly. And I want you to count up all the dumb and uglies. Put little black triangles and all the dumb and uglies on your piece of paper. And then I want you to do the same thing for those that are dumb and beautiful, those that are smart and ugly, and those that are smart and beautiful. All right, so I want you to go ahead and go through that. Let's use these colors. The red triangle is going to be for someone who's dumb but beautiful. The blue triangle will reserve for being smart and ugly. And then the last one, the green, is going to be smart and beautiful. So I want you to go ahead and decode this for me and then come up with the actual numbers. And I want you to put the numbers right here. Okay, all the numbers should go right in there. Okay. Oops, sorry, screwed that up a little bit. We're going to make the, I just realized that capital B is beautiful. So this is, I just need to reset these. Give me a second. Okay, so that's the reset trend there. So I want you to use this code to make sure you go through and reset this. I hope I got you in time before I totally confused you. Oops, sorry. Okay, there you have it. I coded these all up, and you can see here that as a result of this combination, I have this strange ratio. For all 16, I would have 9 that are dumb and beautiful, 3 that are dumb and ugly, 3 that are smart and beautiful, and 1 that's smart and ugly. Now, that's always going to be the ratio, the phenotypic ratio that you see with dihybrid crosses. It's always going to be a 9 to 3 to 3 to 1 ratio. So lock this combination into your brain, dihybrid crosses. Just like we saw with the monohybrid cross, we would have a 3 to 1 ratio. Okay? So this is the most fundamental and basic of the dihybrid crosses. they do get a lot more complex, and in fact, you yourselves are going to look into how much more complex they get. We're not going to do a tri-hybrid cross because that would just get crazy. It just gets progressively bigger, but no different in terms of the outcome. Just gets a little more complex. So, all right, there we have it. I'm going to stop right there. I hope you understood what was going on here, despite the fact that I screwed it up a little bit back there. Bye.